Hello everyone, welcome to the online lecture series of the course EE204 Digital Electronics and Logic Design, Module 5 Synchronous Counters and State Machines. Today we are going to design a Johnson counter circuit. In the last class we have seen a ring counter. A Johnson counter is a slight modification of the ring counter circuit. Here the connections are similar to that of a ring counter, that is, if we are constructing with the help of D flip-flop, the first flip-flop output Q is connected to the D input of next flip-flop and so on, and the complement of last flip-flop output Q bar is connected to the D input of first flip-flop. If we are using a JK flip-flop, the connection is like this. The Q and Q bar output of first flip-flop will be connected to the J and K input respectively of the next flip-flop and so on. And to make the loop connection, the Q bar and Q output from the last flip-flop will be connected to the J and K input of the first flip-flop respectively. And because of this distinct nature in the connection of a Johnson counter circuit, a Johnson counter is also called as a twisted ring counter. The number of states of the Johnson counter will be twice the number of flip-flops you are using. Hence, a Johnson counter circuit is also called as divide by 2n counter circuit. Here, we are going to design a 4-bit Johnson counter circuit using D flip-flop. You can see the excitation table of D flip-flop in the table. On the right side, in the state diagram, you can see the starting state is from 0000, that is the initial reset state. Now, the first flip-flop will be set in the first clock cycle. In the second clock cycle, the first and second flip-flop both will be set, and this will continue till all the flip-flop are set. Here, we are using 4 flip-flops, so at the end of 4th clock pulse, all the flip-flop will be set. From next clock pulse onwards, 1 flip-flop will be resetted from the starting bit. Starting bit in the sense, the bit which is first set in the circuit. So the next clock pulse, the output becomes 0111, and this pattern will continue till all the flip-flops are resetted. Here you can see there are 8 states for a Johnson counter. So we are going to design a 4-bit Johnson counter. So to complete the design, first of all we need to complete the design table. So there are 8 valid states for a Johnson counter. So these 8 states will form the 8 rows of the design table. Starting from 0000 onwards, the last value is 0001. Once you have completed the present state, now you have to fill the next state column. Upon completing the present state and next state, now you have to obtain the required excitations for each of the flip-flop input by comparing the present state and next state of the corresponding flip-flop, and based on the excitation table also. Here also the number of states is less than the maximum number of states. Here there are only 8 valid states for this counter. So the remaining 8 states we have to treat as don't care terms at the time of K-map simplification. On simplification, the K-map for DA is as shown in the left side, and on simplification DA is obtained as QD bar, and the K-map for DB is on the right side, and on simplification DB is obtained as QA. On the left side we can see the K-map for DC, and on simplification DC is obtained as QB, and on the right side we can see the K-map for DD, and on simplification DD is obtained as QC. Now using this minimal boolean expression, the completed logic circuit diagram is as shown in the figure. Now let's have a simulation of the Johnson counter circuit to have a better understanding. So let's check the asynchronous inputs first. Changing the preset to 0 will set all the flip-flop, and making the clear input to 0 will reset all the flip-flop. So initially the counter output is 0000. On application of first clock pulse, the counter output becomes 1000. On the next clock pulse, output becomes 1100. Next clock pulse, output becomes 1110. On the next clock pulse, output becomes 1110. Here you can see for all these clock pulse, starting from the first flip-flop, one by one flip-flops are setting for each of the clock pulse. Now, as all the flip-flops are in the set condition, from next clock pulse onwards, one of the flip-flops will be resetting its state for every clock pulse, starting from the first flip-flop itself. So the next clock pulse, the output is 0111. On the next clock pulse, output is 0011. And the next clock pulse output is 0001, and the next clock pulse output is 0000. That is the initial state of the counter circuit. On the bottom side of the slide, we can see the timing diagram of the Johnson counter. Initially, all the flip-flops are in the reset condition. Output is 0000. On first clock pulse, output changes to 1000, and this process will be continued, and at the end of the 8th clock pulse, the output changes to 0000 again. So I hope with this explanation and simulation, you are familiarized with the design concept and working of a 4-bit Johnson counter.